This video discusses number representation in computers, specifically binary, unsigned, and signed integers. So what kind of number systems do we normally deal with? Our regular number system is a base 10 number system called decimal. Now the decimal number system has 10 digits, 0 through 9. And these 10 digits form the base 10 system. So if we look at an example, this number here, 3,658, we can break it up into its component digits, 3, 6, 5, and 8, right? And if we multiply 3 times 1,000, add that to 6 times 100, and then add that to 5 times 10, and then 8 times 1, we have broken it into the 4-digit components. Looking closely, we can say that 1,000 is 10 to the power of 3. 100 is the same as saying 10 to the power of 2. 5 times 10 to the power of 1 is the same as 10. 5 times 10 is the same as 10 to the power of 1. And 8 times 1 is the same as 8 times 10 to the power of 0, right here. So similarly, we can declare a base 2 example like so. We can also call this a binary representation. Binary representation. And here we have a 6-bit unsigned example here, and we will discuss the difference between unsigned and signed in a moment. So how does this work? We have, instead of using 10 to some power, we're using 2 to some power. So if we have 1, 2, 3, 4, 5, 6 digits, 1, 2, 3, 4, 5, 6 digits, then we're going to need to multiply by 2 to the 5, 2 to the 4, 2 to the 3, 2 to the 2, 2 to the 1, and 2 to the 0. So let's break this down a bit. Let's go through it step by step. 1 times 2 to the 5 here for the first digit. 0 times 2 to the 4. Then we have 1 times 2 to the 3 here. Then we have 1 times 2 squared. Then we have 0 times 2 to the first power. And then we have 1 times 2 to the power of 0. So when we look at 2 to the power of 5, it is 32. 2 to the 4 is 16, but it's multiplied by 0, so it's not added. 2 to the 3 is 8, and it's multiplied by 1, so we add that. 2 squared is 4, multiplied by 1, so we add the 4. 2 to the first is 2, but multiplied by 0, we don't add that. And then 1 times 2 to the 0 is 1. So we add that, and we have 32 plus 8 plus 4 plus 1 gives us a total of 45. Now, an important aspect of binary numbers that we should keep in mind going forward is that we always need to look at the number and declare the number of bits. Must declare number of bits. Because if we don't, then there's a question of what the most significant bit represents. We'll see this in a moment. So binary numbers are also called base 2 numbers, or alternatively we can call them radix 2 numbers. Many other systems are possible, but the on-off nature of CMOS transistors and transistor logic tends to lend itself well to a binary representation. The most significant bit or MSB, is on the left side of the binary number, and the least significant bit, or LSB, is on the right. So MSB left, LSB right. So one neat aspect of binary numbers is that it's possible to represent fractions in binary as well. And we're just going to touch on this briefly here. So let's say we declare a radix point here, and we have a 4-bit integer with fraction following. So we call this a radix point because if we said decimal point, it would imply a base 10, but here we're using base 2, so we use the word or the term radix point. So how do we convert this? The way to convert it is similar to the integer representation. We just extend it a little bit. So we have a 4-bit integer and some bits after the radix point. So we say 1 times 2 to the 3 plus 1 times 2 to the power of 2 plus 0 times 0 times 2 to the 1 plus 1 times 2 to the 0. Now when we go past the radix point, what comes below 0? Negative 1. So we say 0 times 2 to the power of negative 1 plus 1 times 2 to the power of negative 2, and so on. And we can go on for as many bits as we like to get as small a fraction as we want. So what do we get? We have 1 times 2 to the power of 3 for 8, 1 times 2 squared for 4, 1 times 2 to the 0 for 1, and 1 times 2 to the minus 2 for 0.25. I left off the 0 terms because these just drop off to 0. So we can add the power of 2 or not, depending on the binary value. 8 plus 4 plus 1 plus 0.25 gives us a final value of 13.25. So negative binary can be represented with 2's complement. It's quite easy to do this because if we look at the most significant bit, or the MSB, we can declare that as negative and then claim that all other bits are positive. All other bits are positive. So let's look at this example here. How many bits is it? It is 4 bits. Okay? And if we look at the most significant bit, we're going to say that this is representing a negative number. So 2 to the 0, 2 to the 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So negative 1 times 2 to the 3. All other bits are positive or 0, so 0 times 2 squared. Positive 1 times 2 to the first. Positive 1 times 2 to the 0. This gives us negative 8 plus 0 plus 2 plus 1 for a total of negative 5. Now, what's interesting is if we created a 5-bit signed number, we could say 0, 1, 0, 1, 1. And we can see that it is the same as this one is the same as this number over here. But there's a key difference because it's a 5-bit number and it begins with 0 here. So the most significant bit represents the negative number, right? So let's go through this here. We have, for 5-bit, we have 0 times 2 to the 4 plus 1 times 2 to the 3. Notice that this 1 is now no longer the MSB. MSB is 0. So this 1, because it's no longer the most significant bit, we get a positive 1 here. 0 times 2 to the 2 plus 1 times 2 plus 1 times 2 to the 0. So what do we get? We get 0 plus 8 plus 2 plus 1. 8 plus 3 is 11. Different from this number here, negative 5. And all because we declared the number of bits to be different. So bear this in mind. So some examples of binary number conversions that we can do here. How do we convert these numbers from binary to unsigned decimal? Here, let's start with this number. So 0 times 2 to the 6. Oh, I apologize. That is 0 times 2 to the 5 for a 6-bit number, plus 1 times 2 to the 4, plus 1 times 2 to the 3, plus 0 times 2 to the 2, plus 0 times 2 to the 1, plus 1 times 2 to the power of 0. So we have 16 plus 8 plus 1 right here. So 9 plus 16 is equal to 25. So this is equal to 25 here. Let's look at this binary number here. Unsigned. Remember, we're doing unsigned numbers, right? So we have 6-bit, so 1 times 2 to the 5 plus 1 times 2 to the 4 plus 0 times 2 to the 3 plus 1 times 2 squared plus 0 times 2 to the 1 plus 0 times 2 to the 0. So we have 32 plus 16 plus 0 plus 4 plus 0 plus 0 equals what? 16 plus 32 is 48, plus 4 is 52. So we can come over here equal to 52. So now let's look at converting binary to signed integers. So here we need to be cognizant of the number of bits. We are working with 6-bit numbers. Okay? What do we have? 6-bit numbers. Well, we have -1 times 2 to the 5 plus 0 times 2 to the 4 plus 1 times 2 to the 3 plus 1 times 2 squared plus 0 times 2 plus 1 times 2 to the 0. What do we get altogether? Minus 32 plus 8 plus 4 plus 1. So 32 minus 32 plus 8 is minus 24. Plus 4 plus 1 is 5. So we have finally minus 19. Let's look at this binary number now. We have 1 times, or minus 1 times 2 to the 5th, plus 1 times 2 to the 4th, plus 1 times 2 squared. We're just leaving the zeros off this time because we know the 0 bits off this time because we know they add zeros and can be trivially dropped. So what do we have? Minus 32 plus 16 plus 4. So minus 32 plus 16 is minus 16 plus 4. And this is equal to minus 12. Minus 12. Now notice that this number here is the same as this number here in binary representation. However, depending on whether we have an unsigned number or a signed number, the integer value changes because the most significant bit is 1. Let's look at one more example comparing integer or integer conversion between binary signed and binary unsigned. So let's look at the 6-bit number 0, 1, 1, 0, 1, 0. So what about the unsigned value? And what about the signed value? Notice we're still working with 6-bit numbers. So unsigned, we have 0 times 2 to the 5th plus 1 times 2 to the 4th plus 0 times, 1 times 2 cubed plus 0 times 2 squared plus 1 times 2 to the 1st plus 0 times 2 to the 0. So what does this give us? 16 plus 8 plus 2 equals 26. What about the signed version? Well, we have 0 times 2 to the 5 again, plus 1 times 2 to the 4 again, plus 1 times 2 to the 3 again, plus 0 times 2 squared. Notice that only the most significant bit would change in the case of between signed and unsigned numbers. But if the most significant bit is 0, then all other values are the same. So we have 16 plus 8 plus 2 equals 26 again. So if the most significant bit is 0, if MSB is 0, unsigned and signed int values are the same and positive. So bear this in mind when doing number conversions between signed and unsigned and binary and back. So how do we convert a binary number from negative to positive or positive to negative? It's a two-step process where we first flip all the bits. Does this mean this is the same as inverting? So we invert all the bits or flip all the bits, i.e. from 0 to 1 or 1 to 0. And then we add 1, a two-step process. So here's an example using 4-bit numbers. So we have positive 1 in decimal, which is converted to 0, 0, 0, 1 in binary. Let's invert each bit. So we'll start here. 0 becomes 1. 0 becomes 1. 0 becomes 1. 1 becomes 0. Now how do we add 1 to this? Well, we can say 1, 1, 1, 0, and then add 1 to that. So that is 1. And this is basic arithmetic from elementary school. So 1 plus 0 is 1. Carry is 0. 0 plus 1 is 1. Carry is 0. 0 plus 1 is 1. 0 plus 1 is 1 again. And we have our 4-bit number 1111. And once we've done that, we see the value here after adding 1. And this is the same as negative 1 in decimal. Let's verify that we converted correctly. So we have negative 1 times 2 to the power of 3 for a 4-bit number, plus 1 times 2 squared, plus 1 times 2 to the first, plus 1 times 2 to the 0. This is the same as negative 8 plus 4 plus 2 plus 1. 1 plus 4 plus 1 plus 2 plus 4 is equal to 7 minus 8 equals minus 1. And it verifies. Signed addition and subtraction. We can use 2's complement representation for doing addition and subtraction. So say we have a negative 3 added to 7. This converts to 1101 and 0110. in binary. So we can add these two numbers together, 1, 1, 0, 1, and 0, 1, 1, 1, like so. So we have 0, carry the 1 because we have the number 2 in binary. 1 plus 1 is 2, which is the same as 0 in the 1's case and 1 in the 2's column. 1 plus 0 plus 1 is the same as 2, so 0, carry the 1. 1 plus 1 plus 1 is 3, so 1 and carry the 1. Then 1 plus 1 is 2, so 0, carry the 1. And we have a 1 here at the end. But what happens to this? Well, when we're doing signed addition and subtraction here, we need to remember that we need to declare the number of bits in our numbers. These are 4 bits here, right? So this extra 1 just falls off the edge of the world. And we're left with 0, 0, 0, 1, or the number 4. So 7 minus 3 is 4. Because we have a 5th bit here, we ignore that because we're working with 4-bit numbers, 4 bits. Let's look at 3 minus 3. This is the same as adding 3 and negative 3. So you add the 2's complement to subtract a number. Take the 2's complement and add it. So let's take a look. We have 3 and minus 3. You can verify like so how to convert. Convert 3 to minus 3 in binary like so. 0, 0, 1, 1. We invert first. 1, 1, 0, 0. And then we add 1. We get 0 plus 1 is 1. 0, 1, 1. And we see that minus 3 is the same as over here. So now that we've verified that our 3 and minus 3 are properly converted, let's add them. 0, 0, 1, 1, 1, 1, 0, 1. We should get a value of 0 at the end. So 1 plus 1 is 2, so we get a 0, carry a 1. 1 plus 1 plus 0 is 2, so 0, carry the 1. 1 plus 0 plus 1 is 2, so we get 0 and we carry the 1 again. 1 plus 0 plus 1 is 2, so we get 0, carry the 1 again. We have a carry here of 1, but because this is the 5th bit, this is discarded, and we are left with a 4-bit number, 0. And we see 0 is our final result. 3 plus a negative 3 is 0. Now we come to an issue here with 7 plus 4. The maximum possible value that can be represented by a 4-bit number just happens to be the number 7. Maximum possible integer value. Maximum magnitude would be a minus 8. So what happens when we go above 7? We go into the negative range. So let's see what happens. This is binary for 7, binary for 4. I leave that as an exercise to you to verify that these numbers are correct representations. If you don't believe them or you feel a little shaky, I encourage you to try converting them. So 7 plus 4. What do we get? 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 0. Carry the 1 because 1 plus 1 is 2. So 2 in binary is 1, 0. and then 1 plus 0 is 1, and then any carry would be 0. This 0 is ignored here, so we have 1, 0, 1, 1. Notice that we have it the same here, but when we convert it, it becomes -5. Why? Because we have 1 minus 1 times 2 to the 3 plus 1 times 2 to the 1 plus 1 times 2 to the 0. So we have -8 plus 2 plus 1. -8 plus 3 is -5, which is a negative number. A negative number. 4-bit numbers, 4-bit integers, cannot represent a number larger than a larger positive number than 7. So to conclude here, there's also a shorthand way to represent integers that are written in binary, and this is called hexadecimal. Now, hexadecimal is not used in the computer. However, it is very useful when trying to write shorthand by analysis or when typing integers into a programming language. So if you think about a binary number, if you want a number that represents a number, if you want a number represented in the billions range, you're going to need 32, on the order of 32 binary digits. So to represent billions, need 30 to 40 bits. However, that's very inefficient when typing it out. So hexadecimal uses hex digits to represent sets of 4 bits. One hex digit represents 4 binary digits. So it's useful to have this decimal, binary, hexadecimal conversion table. Once you generate this table, you can convert easily between hex and binary. Listed here as well are the signed 2's complement numbers for 4-bit numbers, and we also have an unsigned table. So for hex numbers 0 to 9, A to F. Notice that we use the digits 0 through 9 similar to the base 10 system, and it adds the first 6 letters of the alphabet. And this is used to represent, each digit is used to represent a set of 4 binary numbers. This represents all possible input combination of 4-bit binary numbers. Now if we look on the next slide here, we can see that it extends here. If we want to go above 15 or 15 in integer, or we wish to go above 4 bits, we can go to 5 bits, and we can use multiple hex digits. So from 16 to 31, is represented by 10 to 1F. And if we want to go represent 6 bits, we can go 20 in hex to 2F for 6-bit numbers. And this is a quick introduction to decimal, binary, and hexadecimal numbers for computers.